Some discoveries arrive quietly. A small dip in starlight. A faint distortion in a spectrum. A subtle mismatch between prediction and measurement that at first seems like noise. But every so often, the universe produces a dataset that refuses to settle down, no matter how many times it is rechecked, reprocessed, or reinterpreted. It does not shout. It persists. And persistence, in science, is often more unsettling than anomaly. Roughly 40 light-years from Earth, orbiting a dim red dwarf known as TRAPPIST-1, lies a compact planetary system that has become one of the most closely examined in modern astronomy. Among its 7 Earth-sized worlds, TRAPPIST-1e has emerged as one of the strongest candidates for potential habitability outside the Solar System. Not because it resembles Earth in a straightforward way, but because every new layer of observation seems to narrow the gap between unlikely and possible, without ever fully resolving the uncertainty. TRAPPIST-1 is not a calm star like the Sun. It is a red dwarf, smaller, cooler, and far more active in its early life. These stars are known for intense magnetic flaring, ultraviolet bursts, and energetic particle storms capable of stripping planetary atmospheres, especially during the first billion years of system evolution. On paper, that makes long-term habitability difficult. And yet, the TRAPPIST-1 system has survived long enough for its planets to reach a remarkable state of orbital stability. TRAPPIST-1e sits in what is called the habitable zone, the narrow region where temperatures could allow liquid water to exist under the right atmospheric conditions. But distance from the star is only the beginning of the question. Habitability depends on whether a planet can hold an atmosphere, regulate heat, and maintain chemical cycles over geological timescales. That is where the real tension in the data begins. When the James Webb Space Telescope observed TRAPPIST-1e using transit spectroscopy, scientists were not expecting definitive answers. The method itself is indirect. As the planet passes in front of its star, a fraction of starlight filters through its atmosphere, imprinting chemical signatures onto the light. By analyzing those imprints, researchers attempt to reconstruct atmospheric composition. The initial results ruled out several extremes. A thick hydrogen envelope, like those found on gas-dominated mini-Neptunes, was not present. Neither was a dense carbon dioxide atmosphere similar to Venus, nor the thin, nearly non-existent atmosphere of Mars. What remained was not clarity, but constraint. The data suggested something far more subtle, a possible secondary atmosphere, potentially nitrogen-dominated, with trace components that might include water vapor or methane at very low concentrations. A nitrogen-rich atmosphere is significant because it closely resembles Earth's own atmospheric backbone. Nitrogen does not easily react or break down, making it an ideal stabilizing component. If such an atmosphere exists on TRAPPIST-1e, it could support pressure conditions compatible with liquid water, provided temperature regulation mechanisms are also in place. But TRAPPIST-1e presents a complication that cannot be ignored. It is likely tidally locked, meaning one hemisphere permanently faces the star while the other remains in darkness. This creates an extreme thermal gradient that, in simpler models, would cause atmospheric collapse. One side overheats, the other freezes, and the atmosphere becomes unstable over time. Yet more advanced climate simulations suggest a more nuanced outcome. If the atmosphere is thick enough, global circulation could redistribute heat efficiently. Winds could transport energy from the day side to the night side, smoothing temperature extremes. In such a scenario, the most stable region might not be either hemisphere, but the narrow boundary between them, the terminator zone, a permanent band of twilight circling the planet. Within this region, temperatures could remain moderate enough for liquid water to exist, potentially creating a continuous habitable ring. Life, if it emerged, might not spread across continents and oceans as on Earth, but instead exist in a narrow belt of perpetual dusk. Still, all of this depends on one critical factor: atmospheric survival. Red dwarf stars are notorious for their early volatility. Powerful flares and coronal mass ejections can erode planetary atmospheres over time. However, TRAPPIST-1 is now relatively old and stable compared to its early history. That shift introduces an important paradox. The same star that may have stripped early atmospheres could now be stable enough to allow long-term climate regulation. Another key factor is tidal heating. TRAPPIST-1e does not exist in isolation. It is gravitationally linked to the other planets in the system. These interactions generate internal friction, flexing the planet's interior and producing heat. On Earth, internal heat is largely driven by radioactive decay, but on TRAPPIST-1e, tidal forces could be significantly stronger. This internal energy could sustain volcanic activity, drive mantle convection, and possibly maintain a molten core. A molten core, in turn, is one of the prerequisites for generating a magnetic field. That field would act as a shield, deflecting charged particles from the star and protecting the atmosphere from gradual erosion. If TRAPPIST-1e possesses both tidal heating and a magnetic field, its atmospheric stability becomes far more plausible. And that combination, atmosphere, circulation, and shielding, is precisely what makes it such a compelling target. Yet despite all of this, JWST has not delivered certainty. Instead, it has delivered something more uncomfortable: ambiguity with structure. The data does not collapse into inhabitable or uninhabitable. It sits in between, resistant to categorization. Neither dead rock nor confirmed Earth analog. Future observations are already planned. Additional transits will improve signal resolution and help isolate specific molecular signatures. Scientists are especially focused on confirming whether water vapor is consistently present, whether methane appears in stable ratios, and whether carbon dioxide exists in a balanced atmospheric cycle. Even a small, repeated detection of water vapor would significantly strengthen the case for a temperate environment. But even if all of that is confirmed, habitability does not guarantee life. A planet can meet physical conditions and still remain biologically silent. That distinction is central to modern astrobiology. The difference between a world that can support life and one that actually does. TRAPPIST-1e also raises a deeper temporal question. Red dwarf systems evolve slowly and can remain stable for far longer than Sun-like stars. That extended lifespan means that if life can emerge there, it has far more time to develop complex evolutionary pathways. In theory, such systems could host biological histories that unfold over timescales far exceeding those possible on Earth. This shifts the meaning of the discovery. TRAPPIST-1e is not just a candidate planet. It is a test of persistence. It challenges assumptions about how fragile or common life-supporting conditions really are in the galaxy. In the end, the significance of TRAPPIST-1e is not that it answers the question of life beyond Earth. It is that it sharpens it. It removes excuses of distance, of instrumentation limits, of total ignorance. We are now close enough to analyze the atmosphere of another Earth-sized world in meaningful detail, yet still far enough that every conclusion requires caution. The question remains open, but it is no longer abstract. It is observational. And that changes everything. Because for the first time, the search for life is not only about looking outward into deep space. It is about interpreting what is already within reach, and deciding how much uncertainty we are willing to accept before calling it evidence.